Good afternoon, everyone, and thank you for attending our Smart Heat Trace Design and Installation webinar. My name is Ryan Wood, Content Marketing Manager here at Liberty Electric Products and New England Electrical Sales. Before we get started, I just want to let you all know that you'll be muted during the presentation and we will not be doing a live Q&A. But if you do have any questions as we move along, just enter them into the questions panel, which is located in the webinar control panel, and we'll be sure to reply back to you by email. Also, we will be recording this webinar and we'll post both the recording and slide deck on our website and YouTube channel. Our presenter today is Rob Zerillo. Rob has been in the industrial commercial heating business for nearly 2 decades, first working with the Cleaver Brooks distributor, and then for the last 15 years with Liberty Electric Products, with a focus on electric heating applications. Rob has worked on and developed solutions for more than 500 different heat trace applications in upstate New York. His primary responsibility is being in the field at job sites, working with engineers and architects on new designs, and helping contractors with installations. So without further ado, I'll pass it on over to Rob.
Thank you, Ryan, and thank you everyone for being in attendance today. Really appreciate your time, and for the next hour, we're going to talk a bit more about the 2 most popular heat cables and how we apply them in piping situations. And I hope you get a bunch out of this. I mean, certainly we're very interested in hearing any questions or comments that you have after the presentation. So why don't we dive in, take a quick look at what the outline for this presentation is going to encompass. And, you know, basically we'll go through these 2 most popular heating cables. And I don't want to spend too much time on that segment because obviously I think a lot of it is, you know, how to get into the design process. How's this product going to get put on the pipes, you know, how we basically figure, you know, what goes with what in the controls. So without further delay, why don't we get into our 2 different types of heating cables that are predominantly used in pipe tracing applications. So self-regulating, I'm sure many of you have heard this term before. Self-regulating cable is far and away the most popular heating cable that's used in these applications. What's great about this cable is that it's the only one that can actually, you know, be looped over itself, can touch against itself without burning through, which makes it easy to use out on job sites. They can be cut, spliced, connected out in the field. Pretty easy to work with. You know, they're not the most malleable product, you know, but all things considered, it's a safe bet whenever you're using this stuff with something like CPVC or these transitions from steel to plastic pipes, is that you know, generally you don't have as much precaution to worry about as you would with its relative cousin here, the constant wattage cable. Okay, constant wattage cable is literally exactly what it says it is. I mean, this is a cable that can be also, you know, cut and terminated out in the field. Figuring out circuit sizes when we're dealing with constant wattage cable is a whole lot easier, because again, this is a very constant wattage output, you know, per foot, that makes it very, very predictable, you know, versus the self-regulating nature that can roller coaster a bit with that particular cable. So we'll get into this a little bit more. So when we talk about self-regulating cables, there is an industry standard that all manufacturers abide by as to what or how much heat does this cable put out at the temperature rating of 50 F. So when you see the jacketing of a self-regulating cable where it denotes 5 watt, 8 watt, 12 watt a foot cable, that is what it's delivering at 50 degrees F. Okay, so what happens is with self-regulating cables, they actually work off of a contraction and expansion at a molecular level going on inside of that cable. Okay, and the driver of that is a material called carbon black or irradiated carbon. We're going to see that in another slide here. But basically the content of that cable, how much of it is comprised of that material, is also going to determine how many watts per foot this thing's going to output. Now, the colder you get from 50 degrees F, the more heat this cable is going to deliver. Conversely, as you heat this cable up, it does not want to deliver as much wattage when you heat it up. So that's how it kind of gets its self-regulating name. So low temp self-regulating cable is generally what you're seeing for about 95%, 99% of the market. And what really defines low temp is that it's at an operating exposure temperature of 150 degrees or below. This cable will start to destroy itself around 180 F. So, henceforth, that's always been a great standard to use for things like, say, asphalt shingles when you're doing roof and gutter de-icing, or PVC, CPVC piping when we're doing pipe tracing, because again, that's well below the melt points of either of those materials or any sort of an ignition temperature set point. So again, very, very popular. Medium temp self-regulating cables do exist. Those have a much higher exposure temperature, but again, much more of a niche application. So here's a look at the anatomy, if you will, of a self-regulating cable. If we strip the jacketing off, the outer jacketing, and peeled this guy back. If we start from the inner core and work our way outward, you've got two 16 gauge bus wires, copper nickel stranded bus wires, and they're enveloped by this irradiated carbon or carbon black mixture, which is where all of that self-regulating happens, okay? Then there's a primary overjacket. And originally, when these cables were first invented or put into commercial and industrial use, they were originally designed with just the primary overjacket. These were very popular for doing water piping for trailers, and some of these structures were almost temporary, where, hey, we just got to put a little bit of pipe tracing on this thing to keep it from freezing over the winter time. And basically what was happening during the product's inception was that you get animals or critters in there chewing on that cable, and with no grounding means you could light things up. I mean, there was no GFI code requirement at that point in time. So as the product has evolved, it added the tin copper overbraid layer to it, which is going to help with both cut resistance while you're applying the cable onto piping. And then of course you can also expect different choices as far as the outer jacketing of the cable is concerned. So again, I kind of alluded to the fact that we will not be talking anything about, say, roof and gutter de-icing. The self-regulating cables that are used for that application have UV resistant jacketing on them. Pipe tracing application really doesn't have a whole lot of need or desire for like UV protection, as there's insulation and cladding generally over that pipe. So, generally we're using Teflon or chemical resistant materials for pipe tracing cables. So again, that outer jacket can change depending on your application. So getting back to how that self-regulating cable works. As we discussed, the colder a material is against this cable, what it does at a molecular level is it brings this material closer together. And when it does that, it opens up more electroconductive pathways that create that resistance that heats the cable up. So for instance, if we had a 5 watt-a-foot cable and we put that between 2 blocks of ice and let it sit there for a little bit, it's obviously going to reduce the surface temperature of that cable very rapidly, which in turn is going to heat this cable up, more along its maximum type output operation, which would be up around 10 to 12 watts a foot if this thing was fully encased in snow and ice. As you put this material against a warmer surface, it reduces that wattage output as it pushes those molecules and repels them further away from each other and reduces that wattage output. So you can absolutely have, for lack of a better term, a roller coastering effect across any given length of cable. So if we use a scenario, again, just picture in your head 100 foot of pipe that spans from one building to another building, and it's 55 degrees ambient in building A and 55 degrees ambient in building B, and outside you're at 0 degrees, okay? On each end of the cable that's inside the building, you're going to be putting out, something a lot closer to what the cable's rated at, like either 5 or 8 watts a foot, while outside you could be easily pushing 12 watts a foot. So if there was a piece of that pipe that was exposed in direct sunlight and it was black and you heated the surface of that pipe up to 50 or 60 degrees, in that portion of the pipe, your wattage will reduce. So again, this is an effect that happens across that entire length of cable. When we talk about the circuit lengths, okay, we're gonna touch on this a little bit more in a future slide, but that roller coastering effect and heat from voltage also begins a molecular degradation process on these cables. And we'll touch on this a little bit further in the presentation as well. But generally, a good commercial industrial grade heat trace cable, depending on its use, depending on its voltage, can generally go, and its quality of manufacture, of course, can go typically anywhere from about 10 to 25 years. So there is, again, some separation in quality. And I can at least speak from this perspective is that heat cable is generally one of those things where you get what you pay for. The more premium brands like a Chromalox, they're going to have higher life expectancies and performance on their cables versus, again, maybe a private label option or something that you can get for much less cost per foot. So there is that sacrifice, is that if you're shooting for price, you're generally not going to get the same type of performance for paying the extra. The cables themselves are split into two different voltages. Generally, and again, there are some niche applications where we can get into higher voltages on cables, but 99.5, 99.9% of this market is going to operate between a 120 volt version of a heating cable, and then the other version will be able to handle 208 through 277. But the cable is designed around 240 volt, okay? And the most confusing part about heat tracing, in my opinion, is generally just sizing the circuits, of knowing how much heat cable can you put on each one of those feeder circuits you're bringing out to your job. Okay, so obviously we know that breaker sizes can range from whatever, a 15 amp breaker, a 20 amp breaker, a 30 amp breaker. When we do our calculations, we are basing everything off of 30 amp breakers, because we're looking for what's the most amount of cable we can fit on that circuit. And we'll get into down the road a little bit on the controls, okay? When you have to control these circuits, controlling cost per circuit is another factor that can that can alter the job price a bit. So you'll find out quickly that it's often good to get as much cable on that circuit as you can. So just for an example, here's a chart on your right-hand side that talks about, basically what's the maximum length for a 5 watt a foot cable. Now, basically, if you took 275 feet, so if any engineers are sitting here right now and want to tap this one out, if you took 275 feet and divide that by 5 watts a foot, by your 120 volt, you're going to find at 5 watts a foot that you still have plenty of amperage left on that 30 amp 2-pole breaker. What we have to do is size the circuit for what's the maximum amount of wattage output that cable can put out, and then sizing it accordingly, because we have to deal with things like inrush current. So just as, again, a quick hit, guide as far as how long you can make a 5 watt a foot cable circuit length, here's your different voltages about how far you can max out those circuits based on your voltage. And we're going to touch on this again, so we'll be visiting it a little bit later on in the presentation. Constant wattage cables are different. Constant wattage cables are much easier to size the circuits. They just are what they are. You take 4, 8, or 12 watts a foot times however many feet and divide it by your voltage, and bang, there's your amps. The bus wires are generally a little bit thicker with the constant wattage cables versus the self-reg cables. And the nichrome resistance wire, which I've always found fascinating, is a 37 gauge wire that basically creates the heat inside of these products. So constant wattage is nice because it does have some versatility. I mean, it can handle voltage ranges from 120 up to 480. It can absolutely be cut and field terminated, the whole 9 yards. It handles higher exposure temperatures and can heat to higher degrees as well. But the one big drawback to this particular cable is you absolutely cannot let this cable touch against itself. It will burn through. There is no self-regulating property that backs this thing off before it literally burns right through itself. The other thing is that obviously with, nothing there to kind of put the brakes on the heat output of a cable like this, they are not recommended for using with PVC or CPVC piping systems. So it kind of puts constant wattage a little bit more into a box, but when you're dealing with smaller diameter tubing, like 1 inch, copper or stainless, testing lines, things like that, the overall width of the constant wattage cable is easier to install than a self-regulating cable is. So this really just becomes a little bit more of a, kind of consult your professional rep like us until you get a better feel for exactly what cable you can put on what pipe. So when we look at the anatomy of the constant wattage cable, again, very simple, kind of what you see is what you get. Now, the one thing I will point out is that resistance wire, is spiral wound around the 2 bus wires. the easy way to kind of tell if the jacketing was worn off of the cable, and again, this is not something that's exact. I'm not professing that I can actually look at a stripped cable and tell you, oh yeah, that's a 12 watt a foot cable. But what I do know is that the tighter those resistance wire wraps are, the higher the wattage output of the cable is going to be. If you see a bit more spacing in between those winds, that's going to be a lower wattage output cable. Okay, but generally 4, 8, 12 are your three most popular wattages for a constant wattage product. So we talked a bit about these advantages and disadvantages of each cable. I do like the fact that the constant wattage cables do have a lower inrush current versus the spike you're gonna get typically with a self-regulating cable. So again, you can size your circuits and get usually a lot more cable length on a constant wattage cable job than you could on a self-regulating job. But again, it can be a little trickier in terms of ensuring the fact that you're not touching against yourself. There can't be anything malleable in line that could, potentially disform, melt, or misshape because of the excess heat. When we're talking about metal pipes versus plastic, metal can take all the heat you can throw at it. So generally, we're not too worried about having a safety factor and a little extra heat on a metal pipe. That's no big deal. But plastic, you got to be a little bit more careful with that. So again, great product, works in a ton of different applications, just a little bit more limited. So we'll talk about the fun stuff now and getting into these applications. And the two biggest applications you're going to find with pipe tracing is freeze protection and process temperature maintenance. So the differences between these is, freeze protection is exactly what it describes, right? All we're trying to do is basically keep water or whatever is in that pipe liquefied and keep it from solidifying and bursting that pipe. Process temperature maintenance is a little bit different. Okay, what this is offsetting the losses on the pipe. We don't want to add any heat to the process itself, nor is a heating cable generally the best type of product to do that, because once you consider your flow rates, the diameter of that piping, many times the heat cable doesn't even have enough heat output to get through a Schedule 40 or a Schedule 80 pipe to affect whatever's flowing through it. Okay, but what it does do is it counters those degrees of loss that are coming off the skin of that pipe from point A to point B. And obviously you can figure that the longer those piping runs are, the more potential for BTU loss off of that run is going to be. So basically what we do, are two different calculations that deal with both of these applications. So when we talk about freeze protection, really we're looking at a temperature range that's going to be from roughly -20 to about 40 degrees F. So this is really where we're trying to protect from. Now, in some extreme situations, and again, I don't know if there's any of them that we deal with so much here, even in the Northeast, but you can change that if you want to. If you want to go from a -40 F to 40 F, we can obviously change that threshold. The biggest things that we need to know to correctly figure out what size or what output cable to put on your pipe is your pipe diameter. Okay, your surface diameter of that pipe is going to be directly proportionate to your heat loss. Then what's that pipe made out of? This is PVC pipe, for obvious reasons. We've already discussed this a few times, metal, copper. Once we know this, then obviously this helps us, in terms of knowing how much overage we can put into it, or where we've got to be on that watt loss per foot. And then of course, what voltage do you want to apply to the cable? So, once we've got that, we can basically figure out based on how much thickness of insulation, you're putting around that pipe, how much heat loss you're going to have. So for instance, if we do this calculation, determine on a 4-inch pipe on freeze protection, you're going to add 1.5 inches of insulation. I only need one run of heat trace on a 4-inch pipe. And let's say that comes out to 6.5 watts of loss per foot. So in an instance like that, we're going to recommend an 8 watt a foot cable. It's not grossly overaged, but it will certainly meet the criteria of what that freeze protection has to be. So if that, kind of helps as just a quick makeshift example, that's really what this is. I mean, process temperature maintenance, the only real difference between these two applications, like we still need to know what that pipe diameter is going to be. We still need to know how much insulation you want to put around it. Is the pipe going to be plastic, metal? But the biggest thing is going to be, what is that temperature range? Okay. Again, when we're doing process temperature, we're not going from -20 to 40 degrees. We could be going from what's inside the plant as an ambient temperature of, say, 50 degrees F on average. And this material is going from one side of the plant to the other, let's say, but it has to maintain a temperature of 140 degrees from point A to point B. Well, now my delta T just changed from 50 to 140 versus, say that freeze protection at -20 to 40. So as you can imagine, more degrees, more heat loss, higher wattage cable needs to be put on that pipe to offset those losses. Okay, so again, process temperature maintenance is all about offsetting the losses. Now, we don't want to be grossly over on these as well, because depending on what the material is inside of that pipe, when you're dealing with things like molasses or oil or sugars, things of that nature, we generally we want to make sure that we're not putting enough heat on that pipe to where we can affect what's in it. So again, we're going to try and get a whole lot more spot on to what the actual loss number is. All right, so obviously with design and layout, not a ton of people do this. And, I would say that until you start getting comfortable and confident in doing your own, then certainly, we're extremely happy to take your phone call here and help you with this. As Ryan had mentioned, I mean, I've personally done well over 500, I think, at this point. Our office has done thousands. So, again, there are some, I won't say tricks, but tips to it. Big one being 30 amp breakers. I mean, if you can power these circuits with 30 amp breakers, that's really going to behoove you with less circuits overall, and you can get the most amount of heating cable on that circuit length. So it's definitely the best value, as far as your supply breaker size. Now, one thing that's important to note as well is when we're doing that design, if we went back to our chart from, say, 5 slides ago, and I'm using a 120 volt 5 watt a foot cable that I know maxes out at 275 feet on my circuit length, and let's say from where I'm bringing power inside the plant to where it's got to go in my process is, say, 75 feet. If I'm running just 10 gauge Romex to feed a J box near that pipe, that first 75 feet of pipe and wire does not count against your circuit length. So please understand that. That's a very important note. You're really just totaling up what's your actual footage of heat cable on the circuit, not of supply power. Okay. Voltage we're going to touch on in a future slide here, but voltage plays a big role in your heat output on that cable. We talk about linear pipe runs versus spiral wrapping. So, again, I know that a lot of pictures online that you might look at show spiral wrapping. Well, the math to do a spiral wrap around a pipe is take your pipe diameter times 3.14. And when you start seeing how much more cable that's going to cost you to spiral wrap around that pipe, I'm sure you're going to want to change to linear pretty quickly, because it's going to be about less than half of what you're going to pay to spiral wrap that pipe. And consider, again, what's in it. Is this a pressurized process system? Or is it going to be a freeze protection system where, again, all your fluid is going to be from the, in the lower half of the pipe? Gravity is going to pull that fluid to the lower half. So linear runs 99.9% of the time are better than spiral wrapping. Again, we talked about like metal pipes being able to take all the heat. Plastic pipes can't so much. And then we have what's called a rule of 4 inches, where generally we start butting up against physics and surface area of the pipe. So a piece of self-regulating commercial industrial grade heat cable is going to be about about the same width as a piece of Romex, 12-2 Romex. So again, you can imagine when you're looking at a 12-inch diameter pipe, one little 12-2 of Romex is not going to create enough heat across the surface area to help freeze protect in that application. So we have this rule of 4 inches where generally something like a 4-inch pipe would require 2 or 3 runs at least to properly heat the lower half of that pipe and allow water to keep flowing freely there. So basically aside from that, it's just really the controls that kind of make the differences between these two applications. Whereas with freeze protection, we can use something as simple as an ambient sensing probe outside that says, hey, if the temperature gets to 37 degrees or below, let's kick on all the heat trace circuits. Process temperature maintenance generally uses something like an RTD right on the skin of the pipe to get the exact temperature of the pipe before turning the system on. So this slide is really about the most confusing of the presentation, in my opinion. All right, it really, going back to how do we size these circuits for self-regulating cables. And what I did was inserted a chart here that you would find on the Chromalox CPR cut sheet to give you, an idea of what kind of resources are there for you as well. Some of the charts that we would even reference. And, again, this is what we're pulling from when you call us to ask us a question, is what's really our circuit length max when we're talking about, say, using a 20 amp breaker and I want my startup to happen at 40 degrees F, pipe freeze protection. Well, we can look on this handy dandy chart and tell by what wattage per foot cable it is. If we go all the way down to something like CPR 10-2, and you're going to use a 30 amp 2-pole breaker to power that with, you're looking at a 300 foot maximum length on that circuit at 40 degrees F. Okay. If you notice looking further down that chart, if you tried starting that same cable run up at 20 degrees F, you're only going to be able to put 280 feet on that. So, obviously outdoor temperature plays a big role on when these things start up versus when they don't. But, again, this is the type of resource that we would use to size that out. So take a look at 8 watt a foot cable. Like, whereas we used that example earlier in this presentation, a 5 watt a foot cable draws a maximum of 12 watts a foot. Well, an 8 can draw a maximum of up to 22. So that really kind of changes things as far as how many circuits do we have to, commit to using an 8 watt a foot cable to make sure we can get it all on there without your end user suffering, nuisance trips from GFI pops and, loading up these breakers a little bit too much. So, really, if we, kind of stayed along one of these examples, and in this particular, case, I basically, played a game here with a 750 foot length of 8 watt a foot cable, at 240 volt with 30 amp breakers for freeze protection. So, again, you're going to reference, exactly what I've got circled here as far as, okay, I know that I can use for a freeze protection application. If I'm going to start this guy up at 40 F, I can put up to 420 feet on that circuit length. So if I have 750 feet of piping that I need to do, this is going to commit me to 2 circuits. So I got to have 2 30 amp breakers to send power towards these 2 heat trace circuits. And I can go up to, 840 feet. I only need 750 for my piping, but, again, this is what we would reference so that you knew what you were putting on there. Okay. Now, as far as the part numbers go for Chromalox, as you can see, cable rating, and they've got the part numbers of the cables there. The -1 denotes a 120 volt cable, and a -2 denotes, anything that can basically operate between 208 and 277 volts. So again, that kind of is just one of those things where after a couple of them, you start to figure out, say, the manufacturer, the numbering system, but very quick and easy reference that Chromalox uses. The -1's 120, -2 is basically everything in the 208 to 277 range. So really, when it comes down to it, a lot of the design, it's going to vary tremendously in terms of where do you want to bring power from, where can you bring power from, and where do we set up that first, say J box and start on that pipe tracing. So a lot of this will require some collaboration between, both the specifying engineer, possibly again the rep if they're helping out with that design or doing the design for everyone, and then of course the installing contractor, so that you kind of get all your ducks in a row to make sure that we all know where power is coming in, and we can kind of lay out that design from there. When we talk about voltage, okay, voltage plays a key role in heating cables, and it's amazing how much a few points of voltage can affect that heating cable. So this is where 120 volt, in my opinion, is good. Okay, like 120 volt is a very consistent voltage. The molecular degradation that happens on a self-regulating cable begins at 100 volts, okay, AC or DC. So at 120 volts, you're really not all that abusive on, the heat energy of being applied to that irradiated carbon. And generally a 120 volt cable will last a little longer than its 208 to 277 volt counterparts. When you apply a 208, 277 volt cable, they're generally designed and engineered and built around being a 240 volt cable. So if you feed it with 208 volt, it's going to have a little bit of a diminished wattage output. Okay, so instead of an 8 watt a foot cable now, again, you might be putting out 6.8 watts a foot at 208 volt. You can follow along on the chart there. And then at 277 volt, you're pumping out 8.96. So again, 277 helps you run hot. It's going to take a little bit of life expectancy off that cable. But depending on what your application is, a lot of times, folks generally don't have problem with a little bit more heat versus a little less. And something to consider is that, again, over time, again, this is a 15-year window, 20-year window, you're going to be losing a little bit of wattage output off that cable year over year from that molecular degradation. Doesn't all happen at once. It's not like this thing just hits a life expectancy bell and suddenly dies one day. It's a very gradual degradation of heat over time. So, again, after you've had these cables on your pipes for, say, 10, 15 years, not a bad idea to go out and test them. Make sure that they're still covering you for the application, because obviously the worst case is, you've lost enough cable life to leave this, pipe now vulnerable to freezing. The cable shows it's still working. You're not putting out enough heat to protect that situation, and then there's a problem. Okay, so just something to note there as far as how voltages will affect these cables. When we talk about putting the cable on the pipe itself as well, is with freeze protection, we already kind of touched on it, that all of your fluid is going to be on the lower half of the pipe, especially on horizontal runs. On vertical, it doesn't really make any difference. On a vertical, all I'm going to suggest is stay to the outside of radius bends. So if you've got a 90 and a vertical run, you want to cover you want to run your heat cable across the outer elbow versus the inner elbow. There's more surface area on the outer elbow, much more prudent to put your heat there versus on the inner diameter or the inner radius bend. So, so again, if you look at the graphics over here on the right-hand side, I kind of try to relate it to a clock face. And generally, if I'm out on your job site, you're probably going to hear me say 5 o'clock, 7 o'clock, as far as, things like, where to put the cable on the pipe. Generally, we don't put it flat on the bottom. That was a practice that we got away from about 20, 25 years ago. And the reason being, I mean, it's really not that consequential now, but in some of these process applications where you would either have pipes prone to leakage, things like that, is gravity is going to pull that moisture to the lowest point on the pipe, which is 6 o'clock. So you can only imagine if you've got an electric heating cable that's been sitting saturated in a wet sponge for, I don't know, 6 or 8 months, there is a distinct possibility that at some point, moisture might actually be able to find its way in. So generally we got away from, putting it right directly at the lowest point on the pipe and changing it to 5 or 7 o'clock, if that makes sense. So, again, seems like a pretty common sense type of thing, but, until you got somebody out there who's done this before and knows these little tips and tricks, can be easily overlooked. So, again, biggest thing with putting the cables on the pipes too is your terminations. It's really making sure that you have a quality termination. And, quite honestly, for any, PMs, estimators that might be on this, technicians, I would give yourselves a solid half hour per termination. I know that might seem like a lot, but you can't strip this stuff back and just, slam it in like you can a piece of 12-2 Romex. We talked already about the fact that the bus wires are 16 gauge braided. If you start peeling away some, jacketing of this cable and you're starting to see a bunch of copper filings falling down around your feet, I'd tell you cut that thing an inch back and start over again, because every one of those copper braids is carrying the necessary current that your heat cable is going to need to give you the proper wattage output on the other side of that termination. Okay. We may touch on that a little bit later too. When we talk about process temperature maintenance, sometimes we don't have to play the rule of 4 inches as much as, say, with freeze protection. With freeze protection, we definitely need to make sure that, say the lower surface area of that pipe, stays warm enough to where you're not going to ice inside the pipe and start ganging stuff up inside of there. And we can use things like aluminum tape to help spread that heat across the surface area. With pipe tracing, because it's basically offsetting a loss, a lot of times it's not so much about surface coverage on the pipe as much as it is about just really putting forth the amount of heat required to offset that loss and just maintain the temperature in the pipe. So again, not so uncommon to see something like an 8-inch diameter pipe, if it's in process temperature maintenance, to have just a single run of heat cable on it. Whereas in freeze protection on an 8-inch pipe, I would expect to see at least 2 runs across the bottom of that pipe, to keep things from icing up inside of it. So hopefully that makes sense. All right, when we talk about splicing, really there's kind of 2 things that heat cable does not like, and splicing is one of them and water is the second. Okay, obviously splicing is a necessary thing. Splicing is just as, it's the same thing as connecting power. So, I just made mention that half hour per termination, half hour for a splice. These things really have to be kind of delicately pulled apart. You just don't want to lose those bus wires. And you have to try and get as much of that carbon mastic, that molten carbon that's on the bus wires that creates all that great self-regulating action on the cable. We want to try to strip as much of that off of your actual bus connections as we can. Doesn't have to ultimately be too perfect, but hopefully you can see the bunny ears there in the graphic, those shrink tubing, tubes that you sit at, that are at the bottom of this kit here that would basically fit over the top of your bus wires and eventually be terminated right to the power source. Okay, we always want to make sure that those shrink wrappings are applied correctly, because we don't want arcing going on between the bus wires, while the cable's trying to do its thing. So really good splices take some time. And, when we're talking about doing it on pipes, there's a big difference between using above insulation splice kits and below insulation. Back in the 80s and 90s, it was pretty popular to use under insulation because it was much less expensive, very cost effective, until you had a problem and then you had to find that splice. So that's why we really recommend the above insulation box, because again, this thing sits up on a pipe stub, 4 screws, you can pull the faceplate off it, you can get into that, that splice box and start testing, to find out, hey, is this the bad run? So much more accessible, much more identifiable. We definitely recommend above insulation splices if you have to do it, okay? In some of these cases, while we're doing piping runs, you may run into a situation where there's, say, a T intersection, and if one end of that T might be 10 feet and the other, direction is 60 feet in the other direction, instead of putting a splice there to handle 10 feet of cable with a half hour's worth of labor, we're going to take that cable and run it down 10 feet and then come all the way back with it 10 feet and then go down and do the other 60 feet we have to on the other side. If it's a metal pipe, no big deal. If it's PVC, that's a bigger deal. And we may have to do a splice instead because we don't want to put too much heat on a plastic pipe. But it costs you a whole lot less money and time to run that cable down and back than it would for you to actually complete the splice. And remember that every splice opens up the door to another potential termination issue. So very imperative to do voltage checks, on your splices. Make sure you're getting the same voltage before and after. And if you do, I would also recommend take pictures of your terminations, log those in your job file that you can send off to your PM or to the GC or to the end user. It's just a good CYA policy practice that we'll be touching on a little bit later as well. When we talk about that positioning again on the pipe, this is a pretty good picture that I took off a fire sprinkler system that we had done, I don't know, some years ago, but it actually shows both the down and back on the loop, where you can see that cable in the red circle basically got what we call a down and back. Instead of applying a splice kit at the T, we just basically did that 3 feet, came right back and went down the other side of the pipe. Again, fiberglass tape is going to be your best means of adhering the heat cable onto a pipe itself. This stuff is thin, it's easy to work with, and it can handle the heat. And really all you're looking to do is to, obviously affix the cable to the pipe and to have enough flat surface to surface contact with the pipe itself. So maybe a wind every, let's call it 3 feet to hold it onto the pipe. It just has to, keep it there until the insulators come by, get their insulation and cladding on it. But that's really all that the fiberglass tape does. You can use foil tape as well. It's a great substitute. The foil tape works really well on plastic pipes too, because it helps distribute and spread that heat a bit more. So we talked about the outer radius bend, the state of the outside of the bend versus the inner. But generally, about 2 to 3 feet for your fiberglass tape, something like that ought to give you enough to keep it up on the pipe and easy for the insulators to do what they need to do. When we talk about J boxes and how do we position power out on these job sites, that's a lot of that can be, it's very situational. That's all I can say. I mean, really, without a drawing in front of me or some sort of piping diagram, this isn't the easiest thing to kind of depict through illustration. But what I can say is that, again, what you want to do is kind of position those J boxes to where, hey, I know I can, from this position, get out there and feed this entire run that I need to. And also, if there's, the potential to put more on the pipe, how close are the other pipes to where I can jump over and add some more to this circuit length. So, basically what I'm trying to get you to understand is that, if the maximum length on this example I've got below, using a 20 amp breaker and your length is 330 feet, basically you can run that pipe and wire however many feet out, and that does not count against that overall circuit length. So say I bring J box 1 out there, and I'll just shoot those numbers off the top of my head. Yeah, 120 feet, let's say, of an 8 watt a foot cable. I know I've still got, quite a bit I can put on the circuit length. So now if I come off of the end of that run and I send, just power, I terminate into a J box and then take 12-2 or 10-2 and run that another 50 feet away to a second J box and begin another pipe run. That 50 feet between J boxes is not counting towards my circuit length. So the easiest way to remember it is, if it's heat cable, it counts towards the circuit length. If it's not heat cable, it doesn't count towards the circuit length, okay? So let's talk about controls a bit. We have single circuit controls, which are very popular, obviously, in pipe tracing. A lot of these runs are shorter, and you have different single circuit controllers like ambient, line sensing. Those are your 2 mains. And then, of course, you have these advanced controllers that are, digital, that are HMIs, they're touchscreen, and they can give you a tremendous amount of information. So it really depends a lot on the application. What's the cost threshold of the customer? What do they need the system to do? Those are all things that will determine what kind of controls you want to pick out for it. So generally with a single circuit controller, I mean, say we take an example like a bulb and capillary thermostat, which is your middle picture, with that ambient sensing thermostat, which is the one all the way to the left. We can bring, a 12-2 or a 10-2 right to that thermostat itself, and then come out of the thermostat with our heat cable right on the pipe, and that's done. That's a completed circuit right there. So they can be very convenient, especially for these shorter runs. When you get into stuff like the advanced controllers, if you want to be able to monitor things with BMS, or, this is critical lab stuff here going on, or process, where again, I'm very interested in knowing exactly what the temperature of that pipe is right now, because I can't have it below whatever, 81 degrees or whatever's in it starts to solidify. That's where you're looking at something that's a bit more like an advanced controller that can, give you particular set points and, high current alarms. You can also have the advanced controllers do, ground fault protection, which is a great integrated feature with these. So speaking of that, here's our integrated, Chromalox ITC. This particular electronic controller has a 1 or 2 option, when we send these out to the field, a 1 or 2 circuit option. So basically, long and short of it is the master board is the bottom board. If you open up that control panel cabinet there, you're going to see 2 circuit boards on the right half of the equipment. And the lower board is your master board. The upper board is the slave circuit board. But you can run 2 circuits completely independently with their own line sensing thermostat, out of this particular controller. You can also tie 2 circuits together with a single probe or ambient set point, where again, I can kick on 2 circuits with one control, or I should say one sensor. So there's a lot of different options to customize how you want to use this. What I do like about this particular controller is that it does offer a soft start feature as well, which will prevent you from spiking that inrush current on your voltage and potentially tripping GFI breakers. So, if anything, there are some really nice features and benefits to these advanced controllers, but the one thing that these really kind of are susceptible to are power quality issues. And we're going to talk about that in a second too. So here's a close-up of the display for the ITC controllers. I mean, as you can see, there's quite a bit of information here. And if you look on that one, I think it's the 4th one down, current load, bar graph, and value, when this controller fires up, you'll start to see that black rectangle populate with yellow, just based on how much amperage is basically going into that load. So it's pretty neat that it'll show you like real time of exactly what this thing is drawn and when. Again, you can have alarm histories printed out off of this thing if you want to, or displayed. The one thing I really like, in particular, is that it integrates in the GFI code protection, and it has that soft start feature. Soft start feature will also help extend the life of your cable slightly, because again, you're not whacking it with that full inrush current, when you're applying, heat to your pipe. The programming of these controllers is very intuitive. I mean, it really is very easy. Once you set one of these things up, you could easily fly through these things very quickly. So, I mean, there's 4 buttons on the front face of the unit. Basically, you've got menu, up, down arrows, and enter. So the master code is 0063. That allows you access into anything that can be adjusted on the controller. But when you enter that code on the home screen, you're going to go immediately to menu number 3, the temperature menu. So, you're going to put in your temperature set point, your low alarm, your high alarm. If you've got, a second circuit coming out of that same panel, if it's a 2-circuit ITC, you're going to do the same thing for circuit 2. When you get to the value you want, you hit enter, it saves it. And then basically you can scroll down to the next screen or hit mode button again and flip to screen 4, which is like your current menu. Again, you can go in here, put in your high current alarm. I would recommend not putting in a low current alarm, because really it just becomes a nuisance alarm as that cable begins to ramp up and down. If the ping rate of the controller intersects with where the amperage load is, soft starting the actual cable, and it's right around that 0.2 amp threshold, it's got a pretty good chance of popping an alarm on your controller, which is going to send everybody up in a tizzy over nothing. So, again, because that happens with ramp up and ramp down, I generally disable the low current alarm and worry a whole lot more about the high current, because that's the one you're most interested in anyways. So, what is neat about Chromalox's materials is that you can go into, the installation manual, the ITC controller. You can read up on each one of these fields, what it does. So it does do a really nice job, I think, of giving you those, descriptive definitions. Personally, I won't mess with pages 5 and 6. I'm not a communications guy. I don't really get into things like baud rate and Modbus IP addresses. So I leave that up to the communications guys. I show them how to get there, and then they're very intuitive. They can take care of the rest from where they are. But menu 7 is a good one to be familiar with also, because this allows you to adjust your temperature sensing. So again, if you want to tie both circuits to a single temperature sensor, you do that in this menu 7. You can also change your passwords in here, restore the model if you need to, things like that. So again, I think that if you have the chance ever to get inside of one of these things and start, playing around with them, you'll find that they're extremely easy to function through. When we get into the multi-circuit controls, generally that's going to entail contactor relay panels and then multiple circuit controllers that look a lot like that ITC. Okay, it's just going to be in a larger panel form and with a whole lot more circuits than 1 or 2. So, again, very common for us to have multiple circuits where we're going to need one of these larger control systems out there like that. So I kind of, made a very crude diagram here of how you basically get the signal back to both a breaker integrated, fully, HMI'd, every option available type of panel, or a contactor relay. Both of them start off with a particular sensor. It's either going to be a line sensing sensor or an ambient sensor. And with an ambient sensor, generally, you can go back to either panel with it, but with a contactor relay, remember, if it's a 6-circuit contactor relay panel, then you need to come with 6 30-amp 2-pole breakers out of a distribution panel to wire to those contactors or to the DIN rail inside the contactor relay panel for each one of those circuits. Then you have a controller that interprets the signal from a sensor out in the field. And when it pings and it has a positive, connection established, it'll allow those contactors to close and send power through the unit to your heating cables. The big panel sitting above that entrance panel in our graphics on the bottom of the screen, those are fully integrated breaker loaded manufactured panels by Chromalox, where again, you would not have to bring breakers over. You just bring like a single 100 amp or 200 amp feed into the unit itself, and then it distributes the power. So we'll touch on that in just a second. Contactor relays are built in even numbered circuits, so 2, 4, 6, 8, 10, etc. And you can choose on contactor size between 30 up to 50 amp on the contactors. Well, since we're feeding with a 30 amp 2-pole breaker all the time anyways, generally not a whole lot of reason to go higher on the contactor unless, again, there's a reason for it. So generally we'll set these panels up to have 30 or 40 amp contactors in them. And then we'll use, anything from either a line voltage sensor, or you can use a low voltage sensor. I mean, again, it kind of depends on the application, the end user, what are they looking for out of the system? So, being that these contactor relays also have, GFPE compliance with them, this is oftentimes a much more affordable way to handle that code requirement versus going out and finding dedicated GFI breakers. So again, it's a little bit more work with these because you have to wire each circuit individually over, but very versatile, very affordable. We have tons and tons and tons of contactor relays out there. And it's by far, I think, the most common multi-circuit controller out there. When we look at these advanced loaded HMI breaker loaded panels, sure, nobody loves seeing that price tag in the bottom right-hand corner. I get that. However, this panel is also saving you a tremendous amount of labor time. Because again, instead of having to wire over each one of these 30 amp breakers to a circuit in that contactor relay panel, I just have to bring one big honking feed into this guy, and it distributes all that power internally. So it's a much less time consuming install generally versus contactor relays. The nice thing about these particular panels, again, is that they will tell you if you have a fault, what it is, what circuit it is. So it takes a lot of guesswork out of, when you have issues. The thing that's really the only disadvantage to a lot of, these types of systems that utilize, quite a bit of microprocessor strength is that they can be vulnerable to power quality issues. That's generally the big issue that we run into with them. So, and speaking of power quality, we've been recommending for, years now that any entrance panels or distribution panels that you have feeding power to your heat tracing circuits, you should definitely be looking to put surge protection on it at minimum. And, maybe even thinking about investing some time in either a power quality study, depending on what you've got going on there, because here's something we see realistically, and I know that many people in attendance on this meeting today have probably run into this, is you're going into an industrial facility or a commercial building, let's say that is 50, 60, 70 years old, and that electrical services has been upgraded 3 or 4 times in the last, 6 or 7 decades. So as that service gets upgraded, we're bugging more and more equipment onto it. We kind of lost sight of what's on, what's coming out of this panel, what's coming out of that panel. And there's that potential for signals to cross. So power conditioning, or really trying to make sure you can filter out a bit of that electromagnetic interference, improve your power quality inside the facility itself will only help every microprocessor-based control you have in there. Little quick side note, we actually repped Eaton Power Quality for some years here at Liberty Electric, and I'll never forget the training that we had that, basically 2 points that stuck in my head always was that about 70 to 80% of all your surge events happen from inside the walls of the building, not from the utility side. So again, this is oftentimes the facility being its own worst enemy that creates the problem. The other thing, that I remember was that they said, hey, look, the utility really just needs to guarantee the voltage to your building. It doesn't have to guarantee the quality of that power getting to your building, which is true. So again, whenever you have microprocessor-based controllers, you should be thinking hard about power quality, in my opinion. So, generally we don't have these issues, but it has happened before. And again, typically when you see things like blinking episodes or, chattering on the controller, things like that, it's generally going to be more of a facility power quality thing than the equipment itself. But again, reputable manufacturers and rep agencies like ourselves are more than happy to go out there, help you with those problems and help you determine, what's the issue so we can get it solved and get you back up and running. So let's talk a little bit about installation tips and then we're going to wrap this thing up. So again, when we talk about, planning the job, how do we plan this job out and make sure that we can be successful on our first go around? It really does take a little bit of homework. And, I have noticed that there is a bit of a change in the industry in that, I think 30 years ago, there was a little bit more of that intent of meeting at the job trailer, an hour before the job's going to begin or the week before, or at some point before that project is going to take place where everybody's going through those materials and getting on the same page for a very solid understanding of what's about to happen. And one of the things you're going to want to think of with heat cable is CYA. Okay. I think most of you know what that acronym means. And just to be on the politically correct and safe, professional side of things, I'm not going to define that. It's cover your yes, cover your ass. So at any rate, you want to have a worksheet. Okay. You definitely want to have a record sheet because you're going to want to test voltage. You're going to want to know what that incoming voltage is before you even start to begin putting, heat trace cable on the pipes or putting the controls on the wall. We've seen this happen before where again, we're told that the stated voltage is say 208, the cable doesn't perform well, a lot of complaints start happening, and then we go out there, put a meter on the incoming voltage and find out it's 198, which is going to make a big difference on the heat output of that cable. Okay. Generally, nobody has a problem with it when it's on the hot side. It's the low side we're trying to worry about. Okay. So again, record that voltage to start off with. You also want to measure these cables like crazy. Okay. So again, materials show up. You want to measure these cables, make sure nothing was damaged during the freight, note it. So, again, everybody's aware that, hey, everything was good with this, on such and such a day, such and such a time. When you put the cables on the pipe, you can also do resistance readings. What I would do is don't put your alligator clip across both bus wires at the same time. You always test each bus separately, okay? So that's a great practice to get into with heating cables. And if you're going to measure cables, that's the only proper way to do the measure anyways. Don't try and clip both buses and do it at the same time. Individually check each bus wire, okay? So basically what you want to do is note any of these things that really don't fall underneath your umbrella or that just before the start of it that you notice that could be a potential red flag that might hinder the performance of the system, and just make sure you note it, okay? Generally, it's not going to happen, but again, this is how you prepare for when you get called out afterwards to say, listen, this is what I noticed, this is what I noticed, and this is what I called out, before you're on the hook for any potential problems that could happen down the road. So we talked a bit about cable on the pipe itself, 5 and 7 o'clock positioning of the cable on the piping, larger piping where we're running into our rules of 4 inches there. Do I need more surface area coverage, or is this more of just a process temperature maintenance? But yeah, really when it comes down to it, you're just going to want to take pictures if you can. The more proof you can show before the installation goes on the pipe that, hey, everything was put on this pipe, in its professional manner, how it was recommended to be done. I've got pictures of my terminations. One of the things that I loved, and I've only seen it a very few times in my career is send the 18-year-old kid around, and not hating on any of you 18, 19-year-old younger guys who could be on this right now, but just go and take off those J boxes and let's put a label around the inside of the J box telling whoever takes this J box cover off can see right on the inside cover. Okay, oh great, this 277 volt line, and I have 343 feet of 8 watt a foot heat cable on this. That's great, because now again, anybody who follows your work, they know exactly what's on that circuit, and they know what type of cable it is, again, what its wattage output is. So it literally just, makes life so much easier. So those are the types of things you're going to want to do with heat tracing, because again, most people won't touch this for another 20 years. So good to have a record. Generally when you're doing stuff like, say, valves or obstructions that are inside of the piping runs, you've got to allow for that and put a little bit of slack in that run, so that, again, if the mechanical guy's got to come in here and pull out an OS and Y valve or something like that, they're not going to care about the heating cable. Okay, they're going to try and get that thing off the pipe as quickly as they can without cutting it. But that's not to say it doesn't get manhandled and damaged and scraped and cut, all those types of things. So if we kind of allow them a little bit of slack to say, hey, just take it easy when you take that cable off the pipe, and don't worry, we'll put it back on after. Just, leave it dangling there and don't damage it in the meantime. Well, you can go out there with a Megger tester and test that cable to find out if it was damaged. So your Megger tester really is one of your most valuable tools, in your arsenal. It's your phone, your pen, and your Megger tester. Those are the 3 things you need, and your screwdriver, of course. But again, take pictures, show those terminations, because the other thing that happens is, if there's an issue down the road and it's a question of product quality, or hey, this is defective, whatever the case may be, the factory is going to look for immediate proof. Okay, so that is why it is critical to keep a record of your installations. When we do this, you could forward all of that information, and generally figuring out problems is a lot like a process of elimination. So the more you can do to help yourself on the installation with that CYA policy, the better off you're going to be in the long run. And it also helps to really put you on different footing with your end users, again, because when heat cable goes wrong out on a job site, everybody starts pointing at the electrician or the rep. Okay, so, it's important that we have that body of proof, because instead of having to scramble, lose money on another job because you're, forced to try and get an electrician there within 2 days to react to this issue, that's a whole lot different footing in that discussion when you can say, no, I sent you the job file. We Megger tested everything. We voltage checked everything. We resistance tested everything. We have pictures of our terminations. We have pictures of our installation. It's going to be $250 for me to get out on site, per hour. And the soonest I can get a guy there is a week from now. It just kind of changes the dynamic of that. So always remember, cover your ass in the install. All right. So yeah, if anything, communication also helps with that. Talk to your insulators, tell them that, hey, look, if you guys are going to be putting the insulation on over the pipe and you nick a jacket or something like that, or you think you nicked the jacket, call me. I'll just come over there, Megger, make sure everybody's good before you put all that cladding on, turn this into a really expensive redo. Okay, so just a few tips. Again, if you look for, if you need some more reminders on that, you're always welcome to call us up and, pick our brains for that kind of stuff. We want to see your job go correctly the first time, because we know that A, this is a very versatile product, and B, after you've installed it, say 2 or 3 times, or you've done several designs as an engineer, it's really not all that hard, and your confidence level is going to be directly proportionate to your success. So again, we're absolute volume of knowledge when it comes to these applications, and we want those calls. Okay, so yeah, really when it comes down to it, if you do have some problems on site, obviously you can go back, reread the manuals, retrace your steps, and go through a logical process of elimination. If it seems like it's something more on the material side, then it's, contact and get your distributor or whoever your source was involved. There are some good videos actually on YouTube for terminating heat cables, stuff like that, where again, if you're looking for just a little bit of extra resource and some help, you can pull that phone right out of your pocket on site, and in 5 minutes have a pretty good idea of exactly what that installation's got to look like. And then of course, every one of these manufacturers, certainly Chromalox included, has 1-800 numbers for technical help. Call us. Certainly if you get the cable from us, that's a service we're happy to, support. So, yeah, if anything, our agency's been doing this since '87. We're in our 38th year in upstate New York. We have sold miles and miles and miles of heat trace cable into every application you can pretty much think of. So, you know, if anything, we have some very qualified people in our organization. You know, we've got a fleet of outside guys covering upstate New York and New England. There's a couple of us that are a little bit more proficient than others. The ones who aren't as proficient, they know exactly where to go and who to go to get those answers, and they can get them for you very quickly. So, you know, again, our inside salespeople are absolutely fantastic. And we have what's called an Ed Jordan. We have an engineer who basically resides and does nothing but heat cable layouts, designs, troubleshooting. Ed was a former mechanical engineer that we converted to the good side. Sorry, yes, that was just a joke. Don't get offended. But yeah, no, he's been doing heat cable designs now. I think he's coming up on 9 full years. And he's done probably well over 1,000 himself in that time. So we're calling on architects, engineers, contractors, wholesalers, distributors, you name it. So get us involved. We're happy to help you out on your projects. Please get a hold of us with any questions and any feedback you've got on this presentation. I thank you all very much for your time. Took you 5 minutes past the due date, but hopefully you got a bunch out of this, and we'd love to see you in the future. So thanks again. Have a great Thanksgiving, and hopefully see you in 26.